All right. So, what in particular did you guys?
Well, I honestly on this because I'd never done this before, so I'm just looking at GSG. For me, I'm right now in a battle between Penn State and my vocab, VA, Veteran Affairs.
Yeah.
Books. I don't have my books yet.
Oh, okay.
I know. I like when I pulled up the homework, I was just like, oh. So I can't do the homework yet, and the quizzes. I mean, I did like 2 hours of like research, in which it's my fault. I should have done more studying on the particular subject, but I'm gonna plan on doing this. But I'm kind of screwed right now. I might have to drop out by next week, honestly, if I don't get my books.
Yeah, I understand that. I get it. I have a really crazy semester too. So like is like what like you're looking for just kind of like a general overview? Usually what I do in these, it really depends on the class, but usually what I do is just like go over problems, like how do I think about solving them, and like the problem solving process. Is that kind of what you're looking for?
Yeah, that's awesome. So how often do you do this?
I do this weekly. So every Thursday I will be here, and it will cover
Thursday at 7 o'clock.
Yep.
That's awesome. Okay, I'll put that in my calendar.
Awesome. Well, I'm glad to know that somebody will be here. Sometimes nobody shows up to these things.
That sucks.
Okay.
That's all I really needed. I just wanted to know what this was, actually. I don't have any of my stuff out right now. I got friends over. So
okay.
Yeah, thank you very much. Nice to meet you, Olivia.
Yes, nice to meet you too, Robert.
Jasmine as well.
Nice to meet you too.
Yep, y'all have a good night, okay?
Yep, okay. Good night.
Bye.
All right, Jasmine, it's just you and me. Do you have any questions?
I had a question because I honestly haven't gone over the lesson yet.
That's okay.
I plan on doing it today, but I just thought I'd stop in to see what the group study session. But I had a question from the first quiz. I mean, no, not the first quiz, the first homework.
Okay. Can you tell me what section that was?
Yeah. Sorry, I'm trying to find it.
Yeah, no problem.
It was section 7.1.
Okay.
And it was number 26.
Okay.
And it was a section like E.
Okay. Give me a sec to quick read over 7.1. Oh, this is a lot of notation.
Yeah.
Yeah.
The question I had those, it's like not that related to the exact problem, so I just have to
Okay, I'm looking at the problem right now.
Okay. So it was asking what I think that notation is that A intersects C prime?
Give me a sec. Okay. I think that is referring to all right, sorry, I want to give you like a really good answer, so I don't want to like rush to like an answer. Okay, so we have this universal set that is let's see, where did it go? It is 1, 2, 3, 4, 5.
Right.
And we know, let's see. Okay, I'm kind of looking right now at example 7 on page 361. That's like walking through all the different like parts. So they stated that A, I'm not entirely like
sure on how to
this like notation is not something that I work with a lot.
Okay, that's fine.
So I'm like I don't exactly know how it's like said, but the A
Right.
bar. So your A bar would equal 1, 2, and 4, because those are all of the things in the universal set that are not in A. And we basically find the elements that are, oh geez. Okay, so I think the point of this is to find the elements that are not in common in A, like with the bar on top, and B with the bar on top.
Okay.
That's A and B.
A and C. A and C.
Oh, A and C, excuse me. Yeah, okay.
So it's all of the elements that aren't in set A or aren't in set B or set C.
Okay. I'm sorry.
It's okay.
This is question number 26. Okay, so I did not get the teacher's version of the book for this class, which I'm a little frustrated about, so I can't actually like look up the answer. Okay. So okay. So I think what it's saying is that A so like the A not, the A like under, like not the union. So the A is not in union with C. Those are the ones that they don't have in common.
So it would be 1.
Yeah, sorry, I'm like flipping pages a lot.
So it would be everything that's not 3, right?
Yes.
Okay, that makes sense. Because I did the opposite of that. I think when the professor graded it, he said that, like, I think he said that this notation doesn't equal A union C. So I was like, oh, okay. Or everything.
Yeah. So it's yeah. It's the ones that they, hang on. In this example, okay, so in this example, I'm sorry, I've been making all of these notes to myself. I should be writing this on the screen. Okay. So in this example, we're given, sorry, I'm looking at example 7 still, so I can kind of figure out what's going on. A, B, C, D, E, and F. And set A is equal to A, B, C, and set B is equal to A, C, F. Okay. So what do we know? We know that A bar is equal to D, E, F. We know that B bar is equal to, oh, my handwriting is atrocious today.
Okay.
Sorry about that. Okay, B, D, and E. So what we need to do is, okay, so this is the intersection of A and B is what we're looking for. So the intersection of A and B are the things that A and B have in common. In this case, it is D. Oh, that's bar. Never mind. Ignore that. That's not what we're looking at. We're looking at this one. So in this case, it's A, C. In the example that you were asking about, U is equal to 1, 2, 3, 4, 5. And we are looking for A, C. And this will go. Okay. So we're going to start by saying that, like, it's given to us that A is equal to 3, 5, and C is equal to 2, 3, 4. So what we're actually starting by is finding what a intersection of C is. And
Okay.
so the intersection between A and C is going to be 3. That's not bright enough. Because 3 is in both set A and set C. Okay. That being said, the bar indicates that it's everything but the intersection of A and C. So whatever is in the universal set and is not in the intersection of A and C is going to be this. So this is going to be equal to 1, 2, 4, 5. What are your thoughts? Oh, did we switch to the chat instead of the audio? Yeah, that's no problem. All right. All right. So I am sorry that that took me so long to get around to saying. But let me clear this. And I'm looking through this book and I don't see like any really clear like definitions of things, which is very frustrating to me. Because I feel like there should be like a more like organized like list of like what things mean. But this like U kind of thing is union, and then this is intersection. So this is like if you had two sets, they would be added to one another. So if A is equal to let's see, what was A actually equal to? 3 and 5, and C is equal to 2, 3, and 4. Then union of them is basically like A plus C, or the set is going to be 2, 3, 4, 5. So it's going to be the contents of A and the contents of C. Whereas the intersection is what A and C have in common. All right. I promise you I'm much more prepared for this week's topics. Do you have any specific questions about this week? If you don't, I can just start kind of going off in some of the questions in 7.3. All right. So, for everyone who has their books, we're in section 7.3, Page 376. And we are going to start with question number 1. So a dude has 5 shirts and 3 ties. How many different shirt and tie arrangements can he wear? So, like, how many different combinations of shirts and ties are there? Now, there's a very specific way that they had you try to think about this in terms of, like, P times Q times R, which, like, makes sense, but I don't think you need to, like, have all of the letters there. What I would do is I would start by, like, you guys have worked with tree diagrams, correct? It's something that you did in class. I would make a tree diagram. All right, so there are 5 shirts. And then I would go again and I do ties. And my tree diagrams get a little wonky because I don't want them to overlap. But basically, if we were to go through and we were to count all of these, there would be 15. 1, 2, 3, all the way down, and there are 15 little individual markers. And the way that we get our answer here is 5 times 3. We have 5 shirts times 3 ties. Equals 15 combinations. So yeah, I don't think you need to do the whole shirts is P and ties is Q and then P times Q, because that just kind of adds an extra step. Let's try. Okay. Let's try 15. Um, 15 students log on to the California virtual campus with a username consisting of 8 characters, 4 uppercase letters of the alphabet followed by 4 digits. How many usernames are theoretically possible for this system? Okay, so where would you start? I'm a big fan of writing things down. It's like one of the things that works very well for me, especially when a lot of stuff starts going on. And so I would start by saying character, I just CH, and then I wrote down character 2, 3, and I know that it gives me that there are 8, so I wrote down 5, 6, 7, and 8. And then I went through and wrote down, yes, listing the number of each thing, how many possibilities there are for each one. So for this first one, 26 letters in the alphabet, and because they're all uppercase, it is just 26. 10 possible digits, 0 through 9. And then what we're going to do is multiply them all together. How familiar are you guys? Like, have you been using exponents in class? Because I don't want to like add something extra that you think you need to learn, but Yeah. Okay. Basically, like the whole idea is that we're just going to multiply all of these together, and we're going to multiply all of these together. The point of like an exponent is to say that we're multiplying these, and then we're multiplying these, and then we're at the end we're going to put them all together. But multiplying them out one by one also works. So it's just 26 times 26 times 26 times 26 times 10 times 10 times 10 times 10. And I don't have a calculator on me, so I will not work out what that is. But that is how you solve this type of problem, by listing out how many choices there are. All right, let us talk about number 17 then. So same problem with the username, but now they have no matching adjacent letters or digits. So that just kind of gives us another thing to think about. We still have 26 options for the first one, but here we only have 25 because choice 1 cannot be the same as choice 2. So there are only 25 remaining options. And then for number 3, how many are there going to be? 25, 24, 26. Okay. I can see why you would think 24, and it makes sense. But in fact, although 2 cannot be the same as 3, 3 can be the same as 1. So there's going to be 25 because theoretically these two could be the same. It's the adjacent ones that matter. It would be 24 if things could not be repeated. So again, down here, we're going to have another one that's 25 because 4 cannot be the same as 3, but 4 can be the same as 1 or the same as 2. It's just like, it's a possibility that these are the same letter. And the same thing here. It's 10 for the 0 through 9. This can't be the same as 5. 7 can't be the same as 6, but 7 can be the same as 5. So that's what's possible there. Does that make sense?
I just turned my speak. It's just easier for me to talk.
Okay, yes. But
I am a little confused.
Okay.
So,
Is my notation confusing with the equal sign with the X through it or the cross through it?
no, it's
Okay.
just I think I missed something. Okay, so 2 for the first part.
Mm-hmm.
2 can't equal 3.
Yes.
So 3 can equal 1, but it says 25. So should it be 26 or is 25?
Okay. It should be 25 because 3 cannot be equal to 2. So whatever 2 is, that's off limits for 3.
Okay.
But because 3 can equal 1 again, then it bumps it up to 25. For instance, if 1 was A, 2 was B, then 3 could be any letter of the alphabet but B.
Okay.
And that includes A.
Okay. And because 25 is in 26, it doesn't.
Yeah, and then so it is like every letter of the alphabet. So 26 letters minus the one it can't be, which is
Okay.
B or 1. is 25. And then when we move it down again, if we have A, B, C, then 4. 4 can be any letter of the alphabet but C. So again, it's 26 minus 1, which is the C that it cannot be. And again, that's 25 letters possible.
Okay. That makes sense.
All right. And then it's essentially the same thing with the numbers down there.
Right. Okay. Thank you.
Yep, no problem. Okay. All right. Do you have any like other questions about the process of solving these kind of problems with the like combinations of things?
No.
Okay. Would you like to talk about sample spaces and probability then?
Yes.
All right. Let's start with 9. No, let's start with 7. Did I write down the answer to 7? Yeah, let's just start with 7.
Okay.
All right. So now we are on page 386, problem 7. First, spinner 1 is spun, and then spinner 2 is spun. And the way I initially thought about this is in the form of like a tree diagram sort of thing. So there is spinner 1, and there is spinner 2. So I know from my tree diagram that there's going to be 6 different events. And then I walk down this line, red, green, and then A, B, C, A, B, C. So then each of these different combinations, for instance, maybe red B, red A, red C, each of them is going to be my sample space. So my sample space is going to be equal to, and I'm abbreviating R as red and G as green. R A, R B, R C, G A, G B, G C. And that's my sample space. And so your sample space is essentially just like everything that, all of the possible outcomes that there may be. And then like you start playing with like the different probabilities of all of these outcomes, like later on in this section. Okay, so let's take a look at problem 9 now. This one at spinner 2 is. Were you saying something?
Oh no, I'm sorry.
Oh, sorry. Spinner 2 is spun twice. So there are 3 options. Another 3 options. From our last chapter, we know this means that there are going to be 9 events. What are those events? Sample space is going to be equal to A, B, A, C, A, B, B, C, C, A, C, B, C, C. And that makes 9. My initial question was, when I was looking at the sample set, does AB equal BA? What are your thoughts on that?
I would say no.
You would be right.
Okay.
Because in this instance, it matters the order in which they were
Right.
gotten. So this means that A was first and B was second. And this means that B was first and A was second, and these are not the same thing.
Okay.
So there you go. All right. All right. Let's do 15. All right. Oops. Go. Okay. So this time around, we are tossing a coin 4 times. So the way that we can think about this is, again, I thought about it in terms of kind of like a tree diagram. So you get a heads here, could be heads or tails, heads or tails, heads or tails, and then you can flesh it out. And then do the same for the tails. But what I was most interested in when I was drawing this out is the fact that this is flip 1, flip 2, flip 3, and flip 4. And each of these flips, there are, number 1, they are independent, which is something, did you talk about the difference between independent and dependent probability? I guess you might have talked about it in terms of replacement. If I draw a card from a deck and I don't replace it, it affects the probability of me drawing other cards inside the deck. Because all of a sudden there's not 52 cards, there's only 51 cards. In this case, this is independent, which means that the answer to 1, whatever 1 is, does not affect number 2. So if 1 is heads, then that doesn't mean 2 is any more likely to be heads or tails or anything. There's nothing in the universe that's saying if it was heads once, then it has to be tails next. It's just kind of a most 50-50 kind of we expect 50% of the time for it to be tails, but for all we know, it could just be heads all the time. And it's just random chance. So because these are independent, and there are only 2 options, the way that we can solve this is by multiplying them. You say there are 2 events possible here, times 2 events possible here, times 2 events possible here, times 2 events possible here. So 2 4 times. Another way of writing this in terms of exponents is 2 to the 4th, which is just perhaps an easier way, not necessarily to think about it, but to go from 4 flips to a number. But what this means is 2 4 times. 2 times 2 times 2 times 2. That being said, the answer is 16. Because this is 4 times 4, 16. What are your thoughts on this?
That makes sense.
All right.
Yeah, I understand how exponents work. I'm not sure if anybody else in the class will. That's why I just didn't.
Oh, yeah, no, that's fine. That's just the way that I'm doing this right now. This 2 to the, I'm doing 2 to the 11th or something in one of my genetics classes right now, because of these independent events that can just happen one of 2 ways. So who knows what it's going to be. So yeah. That's sorry. I recognized as I was like reading through this. So I'm like, oh, this is exactly what we're doing. Okay, let's take a quick look at problem 23. And the first one is just asking you, 23 is just asking you which of the probabilities in this sample space are valid and which of them are not. What are your opinions on this? Which ones do you think are not valid? Are there any that are not valid?
I'm trying to look at the chart and understand what's going on.
Okay. So this chart is basically saying that here are the things that happen. Oh, that's HH, excuse me.
Are the letters the number of trial, the trials?
It's like the trial number, letter, it's like this is like the first trial.
Trial A, trial B, trial, yeah.
But okay. It's not that these trials happened. It's that they're asking you which one of these could happen.
Like the most likely.
Most likely, but also even possible. For instance, if you had a loaded coin, are any of these not possible? Is what this question is asking. Oops. So when you're looking at these, do any jump out as not possible? Do you want to just start at the top and work down?
No. Wait. I think the one that doesn't really make sense to me, or the ones that don't make sense to me, are the ones with odd numbers. I don't know.
Okay.
Well, how many flips?
There's only 2 flips.
Right.
So this is the probability of getting heads and then getting heads. And the probability of getting heads and then getting tails. So this is our event up here. HT is heads, tail, or heads, excuse me. I need to rewrite that because I don't know what that is.
Okay, so are they asking us out of A, B, C, or D, and
which one? So they're asking which ones to start off with, which ones are possible, and then which ones are most likely.
Okay. I think the ones that are possible. I don't understand what -1/2 means.
Okay, so that's a good indication that something is wrong there.
Yeah.
You cannot have a negative probability. That's just not how things work.
And B, you can't have 0. If you flip a coin, there has to be something. Or is not that?
Okay, let's start with D. So here we have these negatives that you talked about. That's bad. So this is not possible. Okay. So you are questioning all of these zeros in B.
Yeah.
I will tell you that this is a valid, technically.
Okay.
But the coin is weighted so that you can only get tails.
Okay.
So every time you flip, you're going to get tails. It's going to be tails, tails. You have no chance of flipping heads.
Okay.
And so this basically, the first thing you should look for when you're looking at a probability is that, number one, this is your whole sample space up here. They give you the whole sample space. Just assume that this is the entire thing. Okay. And if the whole sample space probabilities do not add up to 1, then they are not valid. Okay. You cannot do that. Okay. That being said, we know D D is bad, B is valid. Do you have any other thoughts on these other ones?
C is valid because I get all of that would be like would add up to 16.
Yes.
Well, 1 to
Yep.
1. I haven't done that. So E is not valid.
Yep.
And F is valid because that would make 1, right? Did I add that right?
Yep.
Yeah. Okay, that makes when you said that they would all have to equal 1, it just like
Yep.
for some reason it just clicked. I'm like, oh, okay. That
Yep.
makes sense. Yeah.
Because there has to be that 1 is absolute certainty. That's
Right.
why when it's tails, I know that this coin has to be loaded in a way that like makes it always be tails. 1 is certainty, and if it does not equal 1, there is not a certainty involved with the event. Like, I don't know, like if, for instance, in this one, a fourth of the time, like something just doesn't happen. I don't know what that would be. I don't know if like the cosmos open up and like swallow the coin or what. But something is not right when it doesn't equal 1 and the event is certainly happening. And then A, of course, it's just 1/4, 1/4, 1/4, 1/4 is also going to be valid. Which of these do you think is going to be the most logical or like the most like accepted, like if it's not a weighted coin?
A?
Yep. Because it is a 1/2 chance of getting ahead times a 1/2 chance of getting, or like heads, tails, heads or tails. It's 1/4 for all of them,
Right.
and that is simple. Okay. All right. So I think we should do problem 47 next. Okay. So this is kind of an application problem. Families with 4 children are surveyed, and the gender of the children according to birth order is recorded. Construct a probability model describing the experiment, and then find a variety of probabilities. Okay. So the probability model that they want, on 383, they basically define what they want in a probability model as 1, they want you to have defined sample space.
Mm-hmm.
And 2, they want you to assign probability. And so, and like as a subset to that, P of all events equals 1. So that the total probability is equal to 1. I did not see that stated out loud in this chapter, just like very, very definitively. That like probability has to equal 1, and that's like the most, like, that's the easiest way of determining if something's like logical or not.
Yeah.
This is the only place that I found it. But this is very true. The probability of all events together equals 1, which means they're all happening. So, to start with, let's define our sample space. So we have 4 children in each family. That's a given. And we also know that birth order matters. This means that boy, boy, girl, girl is not the same as girl, girl, boy, boy, which is not the same as girl, boy, et cetera, et cetera, et cetera. It doesn't matter that there are 2 boys and 2 girls. What matters is the fact that there are 2 boys and 2 girls, and there are all of these different orders associated with that. So, that being said, how would we go about figuring out how many possible outcomes there are in the sample space?
We could make a chart.
Yes, we could. What kind of chart do you want to make? Just first,
We could do
kind of like this?
yeah.
Okay. And then, oh, jeez. Tablet's not long enough. So the first, we'll just start off saying that they're all boys. Okay. So this definitely works. You could go through and determine all possible combinations like this, but it's going to take a while, and we're going to run out of space. Is there some...
multiply them by well, wait. You could, well, it'll be the same amount of time to do like a tree too, right?
Yes.
So yeah, I'm not sure.
Okay. This kind of relates to what we were doing with the coins earlier. We know that there are 2 options. I visualize this better as a tree. We know that first option is boy, second option is girl, boy, girl, boy, girl. We know that this is event 1, 2, 3, and 4, and each of them only have 2 possible outcomes. And we know that these outcomes don't affect each other. If you had a boy the first kid, you're not any more likely or less likely to have a boy the second kid. So it is going to be 2, oh, that's an E. That's not a 2.
Okay.
I've been, ugh. The other GSG I run is calculus, and I've been doing that for too long, I guess. Okay, so it's 2 to the 4th, or 2 times 2 times 2 times 2, or 16 combinations. And we could see that if we finished out the tree.
That makes sense. Considering there's only 2 options.
Yep.
And then, yeah, 4 trials.
Yeah.
Okay.
So yeah. So that's like where we're going to start by saying that there are 16 possible combinations of boys and girls in like gender distributions and in order of birth. So our sample space is going to be equal to like all of these different probabilities, or all of these different possibilities, excuse me. So from 4 boys to 4 girls and everything in between. Of them, there are 16. Give me 1 second to clear up some of this area so that we can write more. So what does that tell us when the sample space is 16 different things, and we know that they're all independent, like related to one another? What does that tell us about the probability that for like designing a there are 2 parts to a probability model. We found the sample space, but what is the probability of each of these?
They all have to be within the sample space? Well,
Yes, they are all within the sample space. And they are all the same.
Okay.
Because within the sample space, there is no discrimination between, like, it's more likely to have a boy than a girl or anything like that. There is a 1/2 chance of getting a boy, or boy or girl, 1/2 chance of getting another, 1/2 chance of getting another, and 1/2 chance of getting another. So, for instance, if this was just straight boys, it's a 1/2 chance of getting them each time, and this turns into a 1 in 16 chance. Another way of looking at this is saying that there are 16 options within our sample space, and the chance of getting any one of them is 1/16.
Okay.
For instance, like if I wrote down all 16 options and like BB, GG or whatever, and threw them into a hat and pulled one out at random, it's a 1 in 16 chance of me pulling each one. It's not any more likely to do that. Any more likely to be one than the other.
Okay, yeah. They're equal.
Yes. And so thinking in terms of sample space, that's how you think of it. And then thinking in terms of probability of gender, it's 1/2 for a boy, 1/2 for a boy or a girl, 1/2 for a boy or a girl. And like whatever it turns out to be. For instance, if this is BBGG, then it's still 1/16. I can change these letters to be whatever I want them to be, because in the end, it's all 1/16. Okay, so we have our probability model stating that it's 1/16, and because there are 16, it all adds up to 1, so we're good there. We have a probability model. So, find the probability that the first 2 children are girls. How would we go about doing that?
We would have to make it so. Well, I don't know.
Okay. The way I would think about it is in terms of this and not in terms of this. Because there are 2 different ways of like looking at this. You could write out the whole sample set. If you were to do it thinking in terms of like what is the sample like space, you would write out the sample space and find those with 2 girls as first child. Of the first 2 children. In terms of this, I think, okay, so there's a 1/2 chance for a girl the first time. So I'm saying that this represents 1/2 chance of a girl. And this represents another 1/2 chance for a girl. So it's 50-50 whether I get a girl or a boy. But I'm saying I get a girl. And that's what the 1/2 means. And then I don't care what this child is. This could be a girl, this could be a boy, I don't care. So I'm just going to say that's 1 because there is another child. So I'm thinking about these in terms of individual events instead of all parts of a set. Does that make sense?
Yes.
Okay. So I'm going to do the same thing here. Don't care if it's a boy or a girl. I'm going to multiply it out, and it's going to be 1/4. And so if I were to go back and write out all of my sample set or my sample size space, I would find that there are 4 things inside the sample space that begin with G. So The probability that the first two children are girls is 1/4, or in the case of the sample set, 4/16, which is equal to 1/4. Are you okay with me talking about it in terms of the two different like methods of thinking about them?
Yes.
Okay. All right. Then let's think about number 2. All of the children are boys. What is the probability of that happening?
One in 16?
Exactly. There's a 1 in 16 chance of getting the B, and so 1 in 16. And if you thought about that in terms of each birth as a separate event, it would be 1/2 times 1/2 times 1/2 times 1/2. Each of them for a boy in set. Okay. All right. So number 3 is at least one child is a girl. How would you start thinking about this? Yeah.
So, in the event that like a girl doesn't occur, I guess I would exclude.
Yes, exactly. That's exactly it. You start off by saying that we know that things happen. Like, we know that there's, like, everything is occurring. And so, look for events with no girls. We just found out what that was, which was 1 in 16. And so every event that does not have, every event that is not the 1 in 16 that is all boys has at least one girl in it. Correct?
Yes.
So our answer for number 3, at least one child is a girl, is going to be
15 and 16.
Exactly.
Okay.
In terms of individual events, I think looking at the sample spaces would be easier for this one, because I mean, again, you could in terms of individual events, you'd find out what is the probability for boy, 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 and then that would be 1 in 16. And then you would say 1 minus 1/16 is equal to 15/16. 1 being all possible events. In terms of the sets that we were talking about in 7.1, this would be like the U, all possible things going on. Or in terms of just like the S that we have already up here, we shouldn't be adding more letters. This is all of the samples, and this is just B. So that is the sample space. Okay, last one. The first child and the last child are girls. How would we do this? Well, we could look for things in the sample space. where the first child and the last child are girls, and we could count them up. Or we could do what we did for number 1, where the first 2 children were girls. We could say in our individual events that the first child is a girl. There's a half chance of that happening, times 1, where it doesn't matter, and it matters. So a child is born, we don't care what gender it is. A child is born, we don't care what gender it is. Child is born, we care if it's a girl. There's a 1 in 4 chance of that happening.
Mm-hmm.
And here we would look for patterns that look like this.
Right.
Count them up. All right. What are your thoughts on like this process of like analyzing probability for this?
I think it's pretty like easy to understand.
Okay.
Once we went through the examples and like you simplified it, I know that sometimes the text can be confusing, but like,
yeah,
the notes aren't confusing, but the textbook is, because he has like lesson plans and stuff.
Yeah.
And those are easier to understand than the actual textbook.
Yeah.
He has like examples, so that helps. But this also helps me to understand like simpler ways to get to the answer without.
Yeah. I like to focus in GSGs on like ways to solve problems instead of like what does all of this like this notation and stuff mean? Like how can I solve the problem in the most logical manner is my question.
That's
and
that's what we need for the test.
So this is how I would do it, by either thinking about it as individual events or thinking about it in terms of the sample space. Do you have any questions?
Nope.
All right. If you do have any questions, you can email me on Canvas for sure.
Okay.
I check my email very frequently. If that is it, then I think we can hang up for the night.
Okay. Thank you.
So usually these things last about an hour. They might last a little bit longer right before exams if we're doing like an exam review or something like that. But feel free to contact me at any point in time during the week if you have anything that you for sure want to touch on, and I can come up with some interesting examples.
Okay.
So thank you for coming.
Thank you.
Have a good evening.